Okay, so we're going to continue on with the next example where the directions ask us to perform the following index shift. So we're asked to write the sum from 1 to infinity of n squared over 1 minus 3 raised to the n plus 1 power as a series that starts at n is equal to 3. So what I'm going to do, and there are a couple different ways that you can approach this, but I'm going to list out the first few terms of this series. So we get n squared, our formula is n squared over 1 minus 3 raised to the n plus 1 power. So when I plug 1 in for n, we get 1 squared over 1 minus 3 quantity squared, plus when I plug 2 in for n, we get 2 squared over 1 minus 3 cubed, and so on and so forth. Okay, now if I want to start that series at n is equal to 3, where we get an equivalent series, for my first term to be 1 squared over 1 minus 3 quantity squared, what does my formula need to be to get that output? So I need to think about what my formula needs to be such that when I plug 3 into that formula, it's going to give me 1 squared over 1 minus 3 squared. So the numerator would have to be n minus 2 squared, because when I plug 3 into that, 3 minus 2 is going to make the first term's numerator 1 squared, and then my denominator would be 1 minus 3. To get an exponent of 2 on bottom, I need the exponent to be n minus 1. Because when I plug 3 in the place of n, we get 1 minus 3 raised to the 3 minus 1 power, which would give me 1 minus 3 squared. Okay, so this would be what that summation would need to be with the appropriate index shift. Okay, on to the next example, where the directions say to determine if the following series converge or diverge. If they converge, we are asked to find the value of the series. Okay, and we are given the sum from n is equal to 1 to infinity of 9 raised to the negative n plus 2 power times 4 raised to the n plus 1 power. Okay, now what we want to do with this is we want to set our formula up appropriately for, I don't know if you can tell looking at this, but this is going to wind up being a geometric series. We want to set this formula up appropriately for a geometric series. Okay, so it's going to entail me having to like rewrite my formula to put it in the appropriate format. Okay, so this is going to be the sum from 1 to infinity. So I'm going to use a little bit of algebra here to rewrite this. So I'm going to rewrite 9 raised to the negative n plus 2 power as 9 raised to the negative, the quantity, n minus 2 power, which we are multiplying by 4 raised to the n plus 1 power. Okay, if I rewrite things in that way, we get the sum from 1 to infinity. I'm going to rewrite that product as a quotient. So that's equivalent to 4 raised to the n plus 1 power over 9 raised to the n minus 2 power. Okay, so my goal with this is I want to take this, because we're starting at n is equal to 1, I want to express that quotient in terms of the exponent n minus 1. Okay, so in the numerator, I want one of my factors to be 4 to the n minus 1 power. How can I write the quantity on the right equivalent to the quantity on the left? Well, I can take that and multiply it by 4 squared. Because when I multiply two exponents that share the same base, I add their powers. And 2 plus n minus 1 is equivalent to n plus 1. Okay, so these two things here are the same now. They're just written in a slightly different way. And if I want to do the same thing on bottom, if I want a factor of 9 raised to the n minus 1 in my denominator, I can multiply that denominator by 9 to the negative 1 power. Because again, when I multiply two exponents that share the same base, I'm going to add their powers. So that makes these two things equivalent as well. Okay, so what I can do now is I can say that this is equivalent to the sum from n is equal to 1 to infinity. I can rewrite 4 to the n minus 1 power over 9 to the n minus 1 power as 4/9 raised to the n minus 1 power. And then I have these two leftover factors, 4 squared, which is 16, divided by 9 to the negative 1 power, which is the same thing as taking 16 and multiplying it by 9. So we get that equal to 16 times 9, which is 144, times 4/9 raised to the n minus 1 power. Okay, so we have that geometric series written properly now, formatted properly. So since the absolute value of 4/9 is less than 1, the series converges by the geometric series test, and its sum S is equal to A. So the first term of that series is going to be 144 over 1 minus R, which is 4/9, which becomes 144 divided by 5 over 9. And 144 divided by 5/9 is going to be 1296. Oops, 1296 divided by 5. Okay, let's try a similar example. So for the next one, we have the sum from 0 to infinity of -4 raised to the 3n power divided by 5 raised to the n minus 1 power. Okay, so because we are starting the sum at n is equal to 0, we want our exponents to be in terms of n. So I can rewrite this as the sum from 0 to infinity. I can take the numerator and write it as -4 cubed raised to the n power. And then my denominator, I can rewrite that as 5 to the negative 1 power times 5 raised to the n power. Okay, so this is going to become the sum from 0 to infinity. I can rewrite the numerator as -64 to the n power over 5 to the n power. When I divide 5 to the negative 1 power, it's the same thing as like multiplying it by 5. So then I can rewrite this sum here as the sum from n is equal to 0 to infinity of 5 times -64 over 5 raised to the n power. And since the absolute value of -64 over 5 is greater than or equal to 1, then the series diverges by the geometric series test. Okay, so all we are doing is algebraically manipulating our formula to write it with the appropriate exponent for our index or for our starting value of the geometric series. Okay, next set of examples. Ask us to use the results from the previous example to determine the values of these series. Okay, so we said that in a previous example that the sum from n is equal to 1 to infinity of this formula here we said that that was equal to 1296 over 5. Sorry, I gotta plug my battery. Just give me 1 second. Okay. So we said that that was 1296 over 5. Well, how does that series compare to this series? Well, this series here, which is the sum from 0 to infinity of 9 to the negative n plus 2 power times 4 raised to the n plus 1 power, that is going to be equal to the series with the n is equal to 0 term plus this series that we just found right here. So I can go ahead and plug 1296 divided by 5 in for the sum from n is equal to 1 to infinity. Okay, so all I need to do is find the n is equal to 0 term and add it to 1296 over 5. So when I plug 0 into that summation, we get 9 squared times 4 to the first power, which is 81 times 4, which is 324, plus 1296 over 5, and that winds up simplifying to 2916 divided by 5. All right, for number 2, if we're taking the sum from 3 to infinity of 9 to the negative n plus 2 power times 4 to the n plus 1 power, okay, the sum from 3 to infinity of that formula would be the sum from 1 to infinity of that formula. And then from that, we're going to take away the n is equal to 1 term, and we're also going to take away the n is equal to 2 term. Okay, so we know that the sum from 1 to infinity, which we did in the previous example, that's 1296 over 5. We're going to take away the n is equal to 1 term. So when I plug 1 into the formula, we get 9 to the first power times 4 to the second power. And then we're also going to subtract the n is equal to 2 term, which is 9 to the 0 power times 4 to the third power. So this becomes 1296 over 5 minus 16 times 9 is 144. Minus 4 cubed is 64. And that winds up totaling 256 over 5. Okay, on to our last two examples. So directions here say to determine if the series converges or diverges. Then if it converges, we're asked to find its sum. All right, and we have the sum from 1 to infinity of 1 plus 2 raised to the n power over 3 raised to the n power. Now, written in this format, this is not a geometric series, but I can manipulate this formula to make it a geometric series. And I can do that by separating this fraction into two fractions. And I'm going to take the sum of each fraction. So the first way I can do that is by taking the sum from 1 to infinity of 1 over 3 raised to the n power plus the sum from 1 to infinity of 2 to the n power over 3 raised to the n power. Now I want to format these two sums appropriately for geometric series. Okay, so the first one is the sum from 1 to infinity of, I can rewrite that first quantity as 1 over 3 raised to the n power. Plus, we have the sum from 1 to infinity of 2 over 3 raised to the n power. Now, I want both of these sums to have an exponent of n minus 1. So we have the sum from 1 to infinity. I can rewrite that first quantity as 1/3 times 1/3 raised to the n minus 1 power. Because again, when I multiply two exponents that share the same base, I'm going to add their powers. And I'm going to do the same thing for the second sum. So we have the sum from 1 to infinity of 2/3 times 2/3 raised to the n minus 1 power. And then what I'm going to do is I'm going to determine the convergence or divergence of each of those series. Okay, so the first series converges by the geometric series test because the absolute value of 1/3 is less than 1. Second series also converges by the geometric series test because the absolute value of its ratio, 2/3, is also less than 1. Okay, so then we can take the sum, or we can find the sum of each of these series by taking the first term a, which is 1/3, over 1 minus the ratio 1/3. That's 1/3 divided by 2/3, which is equal to 1/2. The sum of the second series would be the first term 2/3 over 1 minus 2/3, which is 2/3 divided by 1/3, which is equal to 2. And then we can add those two sums together. 1/2 plus 2 is going to make 5/2 for the sum up above. Okay, so last example is a telescoping series. And this is where we're going to use the nth partial sum that we talked about at the very start of our lesson. Okay, so this says to determine if the series converges or diverges. And if it converges, we are asked to find its sum. And for this, we have the sum from n is equal to 0 to infinity of 1 over n squared plus 3n plus 2. Okay, so how do you know you're looking at a telescoping series? Well, you know you're looking at a telescoping series is if you can do a partial fraction decomposition. So when I look at this formula here, I can rewrite this as 1 over n plus 1 times n plus 2. All right, so let's do our partial fraction decomposition for this on the side. So we know 1 over n plus 1 times n plus 2 is going to be equal to a over n plus 1 plus b over n plus 2. And then we're going to multiply both sides of the equation by our common denominator. So when we do that, we get 1 equal to a times n plus 2 plus b times n plus 1. And then if we let n equal -1, that means that a is going to be equal to 1. We let n equal -2. That's going to make b equal -1. So I can rewrite this sum then as the sum from 0 to infinity of 1 over n plus 1 minus 1 over n plus 2. Okay, now what we want to do with this is we want to find the nth partial sum. Okay, so what we're going to do is we're going to plug in 0 into that formula, and then we're going to add plugging 1 into the formula. We're going to add plugging 2 into the formula until we get out to the nth term. Okay, so when I plug 0 in first, we get 1 over 0 plus 1, which is 1, minus 1 over 0 plus 2, which is 1 half. Next term we get by plugging 1 in the place of n. So we get 1 half minus 1 over 3 when we do that. Then we're going to plug 2 in the place of n, which gives me 1/3 minus 1/4. Next term would be 1/4 minus 1/5. And then we would keep going until we get out to the last term, which we get by plugging n in the place of n. So we get 1 over n plus 1 minus 1 over n plus 2. And when you do that, you see that negative 1 half and 1 half will cancel, negative 1/3 and 1/3 will cancel, negative 1/4 and 1/4 will cancel, negative 1/5 will cancel with positive 1/5. And then every term is going to cancel until we get to the last term, which is 1 over n plus 2. Okay, so S sub n is just going to become 1 minus 1 over n plus 2. And then we want to take the limit as n goes to infinity of S sub n, which is the limit as n goes to infinity of 1 minus 1 over n plus 2. And as n gets large, 1 over n plus 2 goes to 0. So that limit is 1. Therefore, the series converges and its sum is equal to 1 by the nth partial sum test. Okay, so that's going to be it for section 11-2. Hope you guys have a great day.